Okay, so at the end of the last video, we were talking about what exactly is centripetal force. And so what we came up with was that it's any force that makes an object move in a circular path. So it's really like a category of forces, right? So that gravity can be a centripetal force. Gravity is gravity, but it can act as a centripetal force because there are moments when it's making an object move in a circular path. Same with friction, same with tension. Centripetal force is a net force, so that you have to add up all the forces that are acting towards or away from the center of the circle. And towards the center of the circle is always positive. Away is negative. And if it's not acting towards or away the center of the circle, then it's not a centripetal force and you don't have to include it in the sum. It's not a new force, like I already said, so it's like gravity, friction, etc. And if an object wants to follow a circular path, then there has to be a force acting as the centripetal force. And if that force isn't there, then the object won't follow the circular path. It'll go off tangent to the circle. I'd like to do some examples with you, and I think like examples of, not with numbers, but examples of different centripetal forces. So the first one is, let's think about friction. So imagine it's a snowy, slippery morning, and this is your car, and it's going around a curve. Okay, so your car's going this way, that's the velocity, and so it's counting on a force acting towards the center of the circle that will keep you in this curve. This force, the centripetal force in this case, is friction. Okay, so example 1 is friction. Now, on a normal day, there's good friction, good contact between your tires and the road, and you can zip around this curve quite easily. But on a slippery morning, friction may not be big enough. Remember that centripetal force, this has to be equal to mv squared over r. So the force of friction that you're depending on has to be equal to the speed you're going, the mass of the car, the radius of the car. Well, in any given morning, the mass and the radius are not changing. And remember, if this is a level curve, then this is mu Fn. And if it's a level curve, then this is mu mg is equal to mv squared over r. So the m's cancel, which means it doesn't matter if you're driving a smart car or an SUV, the speed with which you can go around this circle is totally dependent upon the coefficient of friction, because gravity doesn't change and the radius doesn't change. And so on a slippery day, you have to slow down, because if you don't, there will not, the force of friction will not be big enough, and the mv squared over r will be bigger, and you'll go off tangent to a circle. Okay, so that's why on slippery days it's harder to make a curve. All right, a second example would be, think about the sun and the earth. Okay, so here's the earth, and the earth is moving like this. And if the sun's gravity was not acting inward on the earth would go off at a tangent to the circle, right? It would be on its way to a different star. But instead, Fg is equal to Fc. And when we get into the planets in about a week or so, we'll go back to that equation gm1 m2 over r squared that we talked about earlier this semester as the Fg. And that will be equal to, or I think we did, yeah, when we reviewed gravity we did. That has to be equal to mv squared over r. Okay, so one of the m's will go, the mass of the earth. And so the pull of the sun, and one of the r's will go actually. So the pull on the sun on the earth is what's keeping it in its orbit. The speed that the earth is going and how far away the earth is at that perfect balance. So, pardon me, so that the Fg here, the pull of the sun on the Earth, keeps us in exactly the perfect orbit. Okay, so clearly the creator of the universe was the physicist extraordinaire to know exactly how far away the Earth from the sun was and the speed it needed to go to keep these two forces in balance. If it was going too fast, this side would be bigger and it would go off at a tangent. If it was too far away, this side would be smaller and the pull this side would be smaller and the pull wouldn't be big enough to hold it in. So it's in perfect balance here. Okay? So that's gravity. Another one is electrostatic. And that's a unit that's coming, but I know you did a little bit of it in grade 9. So the electrostatic force, and it's FQ. Charge is a Q. Okay, and so think about the nucleus of an atom, which has a positive charge, and the little electron orbiting around the outside has a negative charge. So the electron is going this way, but it is the electrostatic force that's pulling it in here that's acting as the centripetal force. Okay, and we'll do more on that when we get to electrostatics. Another one that is really cool is in an amusement park ride. Now there's a couple of different rides, but first let's assume we're on a Ferris wheel. Okay? So you're sitting on the Ferris wheel. Maybe you're sitting this way, I don't know. Here, here, here. Okay, so here you are. When you're on the bottom of a Ferris wheel, Fg is acting down, and the seat, the normal force, is pushing up. And so the centripetal force here would have to be Fn minus Fg, right? Would be your centripetal force. When you're at the top, it's the opposite. Fg is acting down and the normal force is acting up. And so the centripetal force will be Fg. Remember, towards the center is always positive. It doesn't matter that it's going down. It'll be Fg minus Fn. And when you're over here on the side, then Fg doesn't have anything to do with the centripetal force. It'll just be the back of the seat, the Fn from the back of the seat, that will be pushing you inward. Another ride that's one of my all-time favorites, it's called the Roundup, and it reminds people who go to the Frex of the Gravitron. And I think really its name is the Typhoon. So depending on where you are, Six Flags I think calls it the Roundup, and then places in Florida call it the Typhoon. So what you do is it's a big cylinder, and you go in and you stand with your back against the wall, and gravity acts down. Oh, and they spin you. I should add that. They spin you, and then once you're going at a certain speed, the floor drops away. So gravity acts down, but the normal force isn't acting up. Your back's against the wall. The normal force is acting in. And what holds you up when the floor drops away is friction. And so if you think about it, so the normal force is equal to mv squared over r then, the centripetal force. And so they get it spinning at a certain speed, and then once they do, they drop the floor out, right? So as long as you're going fast enough, the normal force will be big enough so that Fg and FFr, which is equal to mu Fn, are balanced, and then you can stay on the wall. Okay, and then the last one is tension. And for tension, there are two different types. The horizontal circle is easy, and I'll run out of time before I get to the vertical one. In a horizontal circle, when you're swinging a ball in a horizontal circle, the tension is the centripetal force. Gravity is acting down, has nothing to do with towards or away from the center. It's the vertical circle that is special. In a vertical circle, it depends. It's like the or the Ferris wheel. It depends on where you are. Okay, so if I'm swinging something here at the top, both Ft and Fg